transformer overloads are raising concerns amid soaring temperatures. As the mercury rises to unprecedented heights, residents are on edge as the city's power grid struggles to cope with the strain. Firefighters are stretched thin, responding to multiple reports of smoking pole-mounted transformers within a short time span. While the municipal power company frantically works to address the first incident, concerns are mounting about the impending loss of power. The high demand for electricity, coupled with the outdated infrastructure, has created a potential storm for outages. Despite recent efforts to upgrade the primary power lines, the aging transformers appear to be reaching their limits. Residents have noticed crews installing new, larger transformers throughout the town, but time is running out as the heat intensifies. The relentless heat wave has not only exacerbated the situation, but has also cast a shadow over the remainder of the summer. If the power grid cannot withstand the current demand, extended outages may become a daily reality. As the sun continues to blaze, residents anxiously await updates on the transformer situation. The fear of losing power during these extreme temperatures is palpable, and the need for immediate action is evident. Understanding transformer overload requires examining several key factors, including the transformer's design capacity, the ambient temperature, and the load it's currently serving. Transformers are designed to operate within specific temperature limits. Exceeding these limits can lead to insulation breakdown, reduced lifespan, and ultimately failure. The load on a transformer refers to the amount of power it's supplying to connected devices and systems. Overloading occurs when the load exceeds the transformer's rated capacity. High ambient temperatures exacerbate the problem because the transformer has less capacity to dissipate heat. Several factors contribute to transformer overload during periods of high demand. Firstly, increased air conditioning use places a significant strain on the grid. Secondly, population growth and urbanization lead to higher overall electricity consumption. Thirdly, aging infrastructure can struggle to meet modern demands. Lastly, a lack of investment in grid modernization can leave the system vulnerable. There are several steps that can be taken to prevent transformer overloads and mitigate their consequences. Firstly, utilities can upgrade aging transformers with newer, more efficient models. Secondly, they can invest in grid modernization technologies such as smart grids and distributed generation. Thirdly, they can implement demand response programs to encourage consumers to reduce their electricity consumption during peak hours. Fourthly, regular maintenance and inspections can identify potential problems before they lead to failures. Fifthly, implementing proactive load management strategies can distribute the load more evenly across the grid. Understanding the ratings on a transformer nameplate is critical for preventing overloads. The nameplate provides key information about the transformer's capabilities, including its kilovolt-ampere rating, voltage ratings, and insulation class. The kilovolt-ampere rating indicates the transformer's maximum apparent power output. It's crucial to ensure that the load connected to the transformer does not exceed this rating. The voltage ratings specify the primary and secondary voltages for which the transformer is designed. Operating the transformer outside these voltage ranges can damage it. The insulation class indicates the maximum temperature the transformer's insulation can withstand. Exceeding this temperature can lead to insulation breakdown and failure. Monitoring transformer temperature is essential for detecting potential overloads. Temperature sensors can be installed on the transformer to continuously monitor its temperature. If the temperature exceeds a predefined threshold, an alarm can be triggered, alerting personnel to a potential overload. Infrared cameras can also be used to detect hotspots on the transformer's surface, which can indicate areas of excessive heat. Load shedding is a technique used to reduce the load on a transformer during peak demand. This involves temporarily disconnecting non-essential loads to prevent the transformer from being overloaded. Load shedding can be implemented manually or automatically using a load management system. Demand response programs encourage consumers to reduce their electricity consumption during peak hours. These programs often offer incentives for consumers to shift their usage to off-peak hours. Distributed generation, such as solar panels and wind turbines, can reduce the strain on the grid by providing electricity closer to the point of consumption. This can help to alleviate transformer overloads in areas with high demand. Proper ventilation is essential for dissipating heat from transformers. Transformers should be installed in well-ventilated areas to prevent overheating. Obstructions that can block airflow around the transformer should be removed. Forced air cooling can be used to improve ventilation in areas with poor airflow. Routine maintenance and inspections can identify potential problems before they lead to failures. This includes checking for loose connections, damaged insulation, and oil leaks. Oil analysis can be used to assess the condition of the transformer's oil, which acts as both a coolant and an insulator. Surge protection devices can protect transformers from voltage surges caused by lightning or other electrical disturbances. These devices divert the surge current to ground, preventing it from damaging the transformer. Upgrading to energy-efficient appliances and equipment can reduce overall electricity consumption, which can help to prevent transformer overloads. Consumers can also take steps to reduce their energy consumption, such as turning off lights when they are not needed and using programmable thermostats. In conclusion, transformer overloads are a serious concern during periods of high demand. By understanding the factors that contribute to overloads and implementing preventative measures, utilities and consumers can work together to ensure a reliable and resilient power grid. Firstly, regular inspections and maintenance can prevent transformer failures. Secondly, monitoring load levels can help identify potential overloads before they occur. Thirdly, investing in grid modernization and upgrading infrastructure can improve the overall reliability of the power system. Fourthly, promoting energy efficiency and conservation can reduce overall demand. Fifthly, implementing demand response programs can help to shift load away from peak hours. The principles of electrical engineering are fundamental to understanding transformer operation and overload protection. Transformers operate based on the principle of electromagnetic induction, where a changing magnetic field induces a voltage in a nearby conductor. The core of a transformer is typically made of laminated steel, which helps to concentrate the magnetic field and reduce energy losses. The primary winding of a transformer is connected to the input voltage, while the secondary winding is connected to the load. The turns ratio of the transformer determines the voltage transformation ratio between the primary and secondary windings. Protective devices, such as fuses and circuit breakers, are used to protect transformers from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predefined threshold. Grounding is essential for safety and helps to prevent electric shock. Transformers should be properly grounded to provide a path for fault current to flow to ground. The National Electrical Code, or NEC, provides guidelines for the safe installation and operation of electrical equipment, including transformers. Adhering to the NEC is essential for ensuring the safety of personnel and equipment. The NEC Article 450 covers transformers. For example, Section 450.3 covers transformer overcurrent protection. Section 450.11 covers transformer grounding. Section 450.21 covers transformer location. The transformer's kV amp rating is a critical parameter. For example, a 100 kV amp transformer can supply 100 kV amps of apparent power. The apparent power is the product of voltage and current. The real power is the power actually consumed by the load. The reactive power is the power that is stored and released by inductive and capacitive loads. The power factor is the ratio of real power to apparent power. A low power factor can increase the current flowing through the transformer, which can lead to overheating. Power factor correction can be used to improve the power factor and reduce the current flowing through the transformer. This can be achieved by adding capacitors to the electrical system. Harmonics can also contribute to transformer overheating. Harmonics are currents and voltages that are multiples of the fundamental frequency. These harmonics can cause increased losses in the transformer core and windings. Harmonic filters can be used to reduce the levels of harmonics in the electrical system. Transformer oil serves as both a coolant and an insulator. The oil helps to dissipate heat from the transformer core and windings. The oil also provides electrical insulation between the transformer windings and the core. Oil samples should be taken regularly to assess the condition of the oil. Oil analysis can detect contaminants, moisture, and other problems that can affect the performance of the transformer. The dielectric strength of the oil is a measure of its ability to withstand electrical stress. A low dielectric strength can indicate that the oil is contaminated or degraded. The acidity of the oil is a measure of the amount of acid present in the oil. A high acidity can indicate that the oil is oxidizing or breaking down. Dissolved gas analysis, or DGA, is a technique used to detect the presence of dissolved gases in the oil. The types and concentrations of dissolved gases can provide valuable information about the condition of the transformer. For example, the presence of hydrogen can indicate overheating or arcing. The presence of methane and ethane can indicate oil breakdown. The presence of acetylene can indicate arcing or severe overheating. Transformer insulation is critical for preventing electrical breakdown. The insulation is typically made of paper or other fibrous materials. The insulation is impregnated with oil to improve its dielectric strength. Over time, the insulation can degrade due to heat, moisture, and other factors. The insulation resistance can be measured to assess the condition of the insulation. A low insulation resistance can indicate that the insulation is degraded. A megometer is used to measure insulation resistance. The polarization index, or pi, is another measure of insulation condition. The pi is the ratio of the insulation resistance after 10 minutes to the insulation resistance after 1 minute. A low pi can indicate that the insulation is degraded. Transformer tap changers are used to adjust the voltage ratio of the transformer. Tap changers can be either on-load or off-load. On-load tap changers can be adjusted while the transformer is energized. Off-load tap changers must be de-energized before they can be adjusted. Transformer bushings are used to connect the transformer windings to the external electrical system. Bushings must be properly insulated to prevent flashover. Bushing failures can be caused by contamination, moisture, or mechanical damage. Infrared scanning can be used to detect hot spots on bushings. Transformer cooling methods include natural convection, forced air cooling, and oil immersion cooling. Natural convection relies on the natural circulation of air or oil to dissipate heat. Forced air cooling uses fans to force air over the transformer core and windings. Oil immersion cooling involves immersing the transformer core and windings in oil. The oil circulates through a radiator to dissipate heat. Transformer noise can be a problem in some applications. Transformer noise is caused by the vibration of the transformer core and windings. Noise reduction techniques include using vibration isolators and sound barriers. Transformer protection schemes include overcurrent protection, differential protection, and voltage protection. Overcurrent protection protects the transformer from overloads and short circuits. Differential protection protects the transformer from internal faults. Voltage protection protects the transformer from overvoltages and undervoltages. Transformer testing is essential for ensuring the reliability and safety of transformers. Transformer tests include insulation resistance tests, turns ratio tests, and impedance tests. These tests can identify potential problems before they lead to failures. Firstly, it is important to ensure you have adequate overcurrent protection on the primary and secondary sides of the transformer. Secondly, be sure to inspect the transformer regularly for any signs of damage or wear. Thirdly, confirm that the transformer is properly ventilated and cooled. Fourthly, ensure that the transformer is operating within its rated voltage and current limits.